What is up, explorers, and welcome to the edge of what we know. The universe that surrounds us, the vast, near infinite expanse of space and time, is defined by its scale. It is overwhelmingly large, incomprehensibly old, and almost completely, perfectly silent. It is a void of cold, hard vacuum, a darkness punctuated by the pinpricks of ancient light from stars long dead. But every once in a while, out there in that profound stillness, something breaks the silence. Something happens that is so violent, so energetic, that it screams across billions of light years. And today, we are talking about the newest, loudest, and most baffling scream that scientists have ever encountered. This is not going to be a short video. We are embarking on a full, 30-part deep dive into the mysteries that are keeping physicists and astronomers awake at night. This is a journey to the frontier of human knowledge, and we want you to come with us. And because this is such a massive undertaking, we have a special promise. For every single person who makes it through this entire journey to the very end of the final part, we will be making a donation to a foundation that supports STEM education to help build the next generation of scientists who will one day solve these very puzzles. So settle in, grab your beverage of choice. You are going to want to be here for this. It all started in the year 2018. Astronomers began to notice something strange. A mysterious, brilliant blue flash appearing suddenly in the sky and then vanishing. This wasn't just another blip. This flash was and is one of the brightest phenomena the universe is capable of producing. It is an explosion so luminous that it makes an average supernova, the cataclysmic death of an entire star, look like a dimly lit candle flickering in the distance. Since that first detection, more have been spotted. Some have been found relatively close to us, in our own cosmic neighborhood. Others have been detected billions of light years away, their light having traveled for eons from the dawn of the universe just to reach our telescopes. They all look similar enough to be part of the same class of event. But here is the problem. Nobody knows what they are. Nobody knows what could possibly cause them. Through rigorous observation, through painstaking analysis of every photon collected, astronomers began to decode a pattern. They started to formulate a tentative but plausible theory. They thought they were beginning to get a handle on it, until in the year 2023, they saw something new, something that didn't fit, something that left them completely, utterly baffled, and sent them right back to the drawing board. These explosions have a long, technical name: luminous fast blue optical transients. It is an absolute mouthful, so the scientific community has given them an awesome, punchy acronym, LFBOTS. And the key takeaway, the one thing you need to remember, is that there is simply nothing else like them out there. Being such a recently discovered event, the data we have on LFBOTS is, to put it mildly, minimal. The very first one ever detected and confirmed was just 6 years ago. We have only witnessed a small handful since then. And because so little is known, even agreeing on a universal definition of what an LFBOT truly is tricky. For now, what all scientists can agree on are a few common characteristics. These are the fingerprints that all these cosmic crimes seem to share. First, as the name suggests, they all display a predominantly blue emission. In astronomy, color equals temperature. Red objects are cooler. Blue objects are volcanically, impossibly hot. This blue light tells us that whatever this explosion is, it is unleashing a torrent of energy at temperatures far exceeding a normal stellar explosion. Second, they have an extremely high optical luminosity. They are, simply put, blindingly bright. Third, they are not just bright in the visible light our eyes can see, they are also glowing powerfully in other parts of the spectrum. When our telescopes look at their locations, they see them shining in X-rays, in ultraviolet light, and even in radio waves. This multi-spectrum glow tells us that a wide range of incredibly high-energy physical processes are all happening at once. And fourth, they are fast. Again, the name says it all. LFBOTS go off like a cosmic camera flash. They rocket from nothing to their peak brightness and then dim back into nothingness with incredible speed, usually in the space of just a few hours or, at most, a few days. Now, you might be thinking, that sounds just like a supernova. But it's not. A supernova follows a similar pattern of brightening and dimming, but its dimming process is a graceful fade-out. It takes weeks or sometimes months to fade away. An Elphrabot is a cosmic cracker. It is here and then it is gone. This transient or short-lived nature is precisely what makes them so difficult to spot and even harder to study. So, if they are so fast, how did we ever manage to capture one?
So, if these LF bot events are so incredibly fast, vanishing in just a few days, how did we ever manage to capture one in the first place? The answer lies in a new generation of robotic telescopes. We no longer live in an age where an astronomer sits at an eyepiece all night. We now have machines that do the watching for us. Enter NASA's Atlas HKO telescope in Hawaii. Now, Atlas is not designed primarily to find new cosmic explosions. It's part of an early asteroid impact warning system. Its mission is to protect Earth. To do this, it scans the entire visible sky every single night, multiple times. It's a relentless wide-field camera that takes a snapshot of the sky, then another and another. It then uses powerful software to subtract the images. It looks for anything that has changed, any dot of light that wasn't there before, or any dot that has moved. Usually it finds asteroids, but on the night of June 16, 2018, Atlas HKO was performing its routine scan when its software flagged something very unusual. A new dot of light had appeared in the Hercules constellation. But this wasn't the slow, steady streak of an asteroid. This was a brilliant stationary flash, and it was bright. It was recorded as being over 100 times brighter than our regular supernova. And then, within just a few days, it was gone. The scramble was on. This is what astronomers live for. An alert was triggered, sending an automatic message to telescopes all around the world, both on the ground and in space. It was an all-hands-on-deck cosmic emergency. Everybody, stop what you are doing, point your telescopes at these coordinates right now. Scientists immediately began analyzing the flood of new data. They pinpointed the explosion's location. It was coming from a galaxy about 180 million light-years away. In cosmic terms, that's in our backyard. It was officially designated AT 2018 COW. The AT stands for Astronomical Transient. But the COW at the end, part of the random naming system, was too good to pass up. The event was affectionately nicknamed forever as the COW. Once located and observed by this fleet of telescopes, the first job was to classify it. What was it? The default assumption for any massive explosion is a supernova. Based on the light it was giving off, it was quickly classified as a Type 1b supernova. Now, a quick astrophysics lesson. A Type 1b supernova is a core collapse explosion. It's what happens when a truly massive star, a star many times the mass of our Sun, runs out of fuel. But specifically, it's a star that has, before its death, already lost its outer envelope of hydrogen. The star's own powerful winds have blown it all away. So when it finally explodes, we see the signature of what's left, mostly helium. But there was a problem. Something about this particular explosion didn't quite fit the Type 1b profile. When scientists looked at the spectrum of the COW, the rainbow of its light broken down into its chemical fingerprints, it didn't look typical. It had unusually broad emission lines. This broadness tells astronomers that the material is being ejected at insane speeds, much faster than a normal supernova. And it had very weak helium lines. It wasn't the clean helium signature they expected. This wasn't a textbook case, so scientists thought it might be something else. The first classification as a Type 1b supernova was shaky. The weak helium lines and the incredibly broad features in its spectrum suggested it was something more. So, it was quickly reclassified. The next logical step was a Type 1c BL supernova. Let's break that down. A Type 1c supernova is a star that has lost both its outer hydrogen and its next layer of helium. It's a star that is peeled down to its bare core of carbon and oxygen before it explodes. The BL part stands for broad-lined. This means, just like the cow, that the material is being ejected at extreme velocities, often at a significant fraction of the speed of light. These Type 1c broad-lined events are the rarest and most energetic supernovas we know of. In fact, we believe that this is the type of explosion that is powerful enough to create a long-duration gamma-ray burst, one of the most violent events in the universe. So, by reclassifying the cow this way, astronomers were saying it was one of the most powerful stellar deaths imaginable. This seemed to fit for a moment, but the more scientists pored over the data from all those different telescopes, the more surprised they were. Because whatever this explosion was, it started to look less and less like any kind of supernova. At least, not any kind of supernova we had ever seen or modeled. The Type 1c broad-lined label was just a box, an attempt to fit a square peg into a round hole. The data was telling them this was something new. For starters, it appeared out of nowhere. We keep saying it was fast, but it's hard to overstate what that means. This blast went from an inactive, invisible state to its absolute peak luminosity, brighter than 100 supernovas, in just 3 days. As we mentioned, a typical supernova takes weeks, even months, to slowly ramp up to its brightest point and then dim again at a similar, leisurely pace. The cow was not a slow burn, it was a detonation. Not only that, it was registered to be 10 to 100 times brighter than an ordinary supernova. Where was all of this energy coming from? How was it released so efficiently? And then there was the way it exploded. Everything about its shape was wrong. When supernovas explode, they tend to release their energy in a roughly spherical shape. Think of a bomb going off. The shockwave expands outwards in a more or less uniform ball. Now, we've known for a while that the shockwave can be aspherical, meaning not perfectly round. This can be caused by the star's own rotation or the presence of strong magnetic fields, which can channel the blast and distort the shape. But upon closer inspection, this mystery explosion did not even try to be spherical. The researchers themselves, in their published papers, called it the most aspherical explosion ever seen. It was dramatically one-sided. It was as if the star had jetted its energy out in one direction, like a cosmic cannon, rather than exploding like a bomb. This wasn't just a slight distortion. This was a fundamentally different kind of explosion. The tidy supernova explanation was falling apart, fast. The cow was too bright, too fast, and too weirdly shaped to fit any existing model. The universe had just thrown a major curveball. With the supernova theory failing, scientists had to get creative. They were back at the drawing board, looking for any physical mechanism that could explain this bizarre combination of features: extreme brightness, blinding speed, and a highly non-spherical shape. Soon enough, new theories were being put forward. The first, and one of the most popular, was that the cow was not the death of a star, but the murder of one. The culprit? A monster black hole. This scenario is called a tidal disruption event, or TDE. It's what happens when an unlucky star wanders too close to a massive black hole. The black hole's immense gravity seizes the star. But the gravity on the near side of the star is so much stronger than the gravity on the far side that the star is literally pulled apart like spaghetti. This process, called spaghettification, is incredibly violent. The stellar material is ripped from the star and forms a swirling superheated disk, an accretion disk, around the black hole.
As this material spirals into its doom at nearly the speed of light, friction and magnetic fields heat it to billions of degrees, causing it to unleash an enormous flash of light, especially in X-rays and ultraviolet. This theory had a lot going for it. It could explain the brightness. It could explain the blue, hot color. But it had problems. The timing was wrong. The light curve, the way the event brightened and faded, didn't match our models for a TDE. A tidal disruption event should rise to brightness relatively quickly, but its fade out, as the material is slowly consumed, should be much more gradual, lasting for months or even years. The cow was gone in days. It was just too fast. So, theory number 2 was proposed. Others suggested that the cow was a supernova, but a very special engine-driven kind. Perhaps it was a collapsar. This is a scenario where a massive star collapses, but instead of the explosion succeeding in blowing the star apart, it fails. The core collapses directly into a black hole, while the star's outer layers are still falling in. This new baby black hole, spinning rapidly and fed by the star falling onto it, forms an accretion disk inside the star. This engine then launches 2 incredibly powerful focused jets of plasma out of the star's poles. These jets, like a blowtorch, rip through the star and slam into the surrounding space. This would perfectly explain the most aspherical explosion ever seen. It would be a jet, not a sphere. It would also be incredibly bright. This was a compelling theory, but let's step back for a moment. All of this complex modeling was based on one object. It is really hard to draw any universal conclusions when you only have one of something. As the old saying in science goes, once is an anomaly, twice is a coincidence, and 3 times, that's a pattern. We had a cosmic monster, the cow, but a single data point is just a story. It's a curiosity. To do real science, to actually understand this new class of object, you need a pattern. What researchers really needed, more than anything, was a bigger sample size. They needed more examples of this kind of explosion. They needed to compare observations to find common threads and to deduce any patterns that might arise. They needed to find another cow.
Luckily, the universe did not make them wait long. The same robotic surveys that had caught the cow were still scanning the sky, night after night. And with astronomers now knowing what to look for, a flash that was intensely blue and incredibly fast, their software was updated to find them. Just a few months later, in September of 2018, the cosmic camera flashed again. The Zwicky Transient Facility, or a ZTF, another robotic sky survey, picked up an object named ZTF-18ABUKAVN. It was another ELF-bot. It was nicknamed the Koala. It too was bright, blue, and fast. And then again, a third time in 2020. Another was found, this one nicknamed the Camel. And just like that, within 2 years, astronomers had data on 3 separate ELF-bot events. The anomaly had become a pattern. The cow was joined by the koala and the camel. A new ELF-bot zodiac was being born. Now, finally, they could start doing comparative science. They could hunt for patterns. When analyzing the cow, the koala, and the camel, one of the first and most striking things that stood out to researchers was not their light, but their location. Even though all 3 explosions happened in completely different parts of the universe, light years apart, they all shared one critical feature. Each blast was registered as coming from inside the spiral arm of a galaxy. This was a very big deal. At first, this information powerfully emboldened the initial discarded theory. that ELF bots were in fact just a very special type of core collapse supernova. Let me explain precisely why this location is such a critical piece of evidence. To understand this, we have to understand what spiral arms are. If you picture a beautiful spiral galaxy, like our own Milky Way or Andromeda, the spiral arms are not solid structures. They are density waves. Think of them as a cosmic traffic jam. As gas, dust, and stars move through the galaxy, they enter this wave and slow down, getting compressed. This compression of gas and dust is what triggers massive bursts of new star formation. So the spiral arms are the bright, swirling lanes filled with hot, young blue stars. They are quite literally the stellar nurseries of the galaxy. This is where almost all new stars are born. And the kind of star that causes a core collapse supernova is a massive star, one of the biggest, hottest, bluest types you can get. These are the O-type and B-type stars. And as you know, the bigger the star, the shorter its lifespan. Our Sun, an average star, will live for 10 billion years. These massive stars, they are the rock stars of the universe. They live fast, they burn through all of their nuclear fuel at an incredible rate, and they die young in a spectacular, violent explosion. Their entire lives might only last a few million years. A few million years is on a cosmic scale nothing. It's the blink of an eye. This means that these massive stars do not have time to travel very far from where they were born before they die. They are born in the spiral arm, and they die in the spiral arm. This is why the location was a smoking gun.
The location for all three alpha bots, the cow, the koala, and the camel, was a perfect match. All three were found nestled deep inside the active, star-forming regions of their host galaxy's spiral arms. This was precisely where you would expect to find the deaths of massive, short-lived stars. This new evidence seemed to resurrect the core collapse supernova theory from the dead. But it had to be a special kind. The data from the cow had already proven that it couldn't be a normal explosion. It was too fast, too bright, and too asymmetrical. So, what kind of massive star could die in such a peculiar way? The scientific community began to converge on a new, more specific theory. This was not just any core collapse supernova. This was likely the death of a truly exotic kind of star. Perhaps a Wolf-Rayet star, a massive star that has already blown off its hydrogen and helium layers, leaving a bare core of heavy elements. Or perhaps it was a star that had been stripped of its outer layers by a binary companion star, in a kind of cosmic vampirism. Whatever the specific case, the underlying story seemed to be holding. A massive star dies. The location data was so strong that it was hard to argue against. The mystery, it seemed, was finally being solved. Or at least the big picture was coming into focus. Alpha bots were not some brand new, bizarre physics like a black hole eating a star. They were simply a new, extreme, and very rare subclass of core collapse supernova. Maybe something about the star's incredibly fast rotation or an ultra-powerful magnetic field was creating the engine that drove those high-velocity jets. This would explain the asymmetrical shape of the cow and the extreme brightness. The scientific community breathed a collective, tentative sigh of relief. The puzzle seemed to be fitting together. The answer was neat, tidy, and satisfying. It connected back to what we already knew about the life cycle of stars. But the universe, as it always does, was not finished with us. It was holding another card up its sleeve. Just as researchers were getting comfortable with this new, exotic supernova model, something else happened. Another robotic telescope, another scan of the sky caught another flash. And this one made no sense at all. It was about to catch them completely off guard again.
The Zwicky Transient Facility, or ZTF, our relentless change detection machine, was still watching. In the year 2022, it detected another, similar explosion. It had the right color. It had the right brightness. It was immediately flagged as a new AlphaBot candidate. But after that initial blinding flash, this new optical transient started to behave rather strangely. Instead of exploding once and then fading away into darkness over a few days, like the cow, the koala, and the camel had done, this new one, nicknamed the Tasmanian Devil, didn't stop. It continued to produce short-duration bursts again and again long after it should have been gone. What was even more bizarre, each of these subsequent bursts seemed to be just as bright, just as powerful as the original explosion. This was very, very strange. The Tasmanian Devil was recorded as emitting more energy than hundreds of billions of stars like our Sun combined. Researchers were deeply, profoundly puzzled all over again. This was not in the script. It was unlike anything they had ever seen in the history of astronomy.
Now, I know what the skeptics among you must be thinking. Alex, you're saying, this has got to be a mistake. A technical error, a sensor glitch, a miscalibrated instrument, a fluke in the quality control tests, or maybe just a simple mathematical mistake. And that is a perfectly reasonable, scientific, and healthy thing to think. In fact, it's the first thing every scientist on the team thought. The history of science is absolutely littered with moments just like this. Scientists shouting "Eureka" at supposed breakthroughs or paradigm-shifting discoveries, only to be quietly and embarrassingly deflated once someone double-checked their work, or found a bug in the code, or realized a sensor was unplugged. It happens all the time. It is part of the process. But this is not one of those moments. This was not a fluke. The data was immediately and independently corroborated by 14 other telescopes around the world. Telescopes in different countries, run by different teams, using different hardware and different software, all pointed at that same patch of sky. And they all saw the same thing. The Tasmanian Devil was, in fact, pulsating. It was flashing. It did this a minimum of 14 confirmed times over a period of weeks. The total unconfirmed number of bursts was likely much, much higher. This was real. The data was solid. Equally as surprising as the bursts themselves was their timing. These were not small, flickering aftershocks. These were mega-powerful pulses, each as bright as the original explosion, and they were separated by mere minutes. To the scientists watching, it looked like a star that just refused to die. It looked like a star that kept dying and then being miraculously revived over and over and over again. This was, to put it lightly, a major problem for our exotic supernova theory. Supernova are a one-time event. It is the final, singular, cataclysmic end of a star's life. A star does not, cannot keep exploding. It's a one-and-done catastrophic failure. Yet here was an object behaving like an elfbot that was doing just that. If this is what it appears to be, this strange pulsating phenomenon could provide a brand new revolutionary insight into the life and death of stars. So far, stellar life cycles have only ever been studied as snapshots. We see a star in its youth, we see a different star in its middle age, we see a different star in its death throes. We piece these static photos together to create an album of a star's life. We have never been able to watch a continuous process of a star's final moments, let alone one that seems to stutter and restart. So, in short, even though the multiple bursts of light from the Tasmanian Devil were completely unexpected, they still didn't completely kill the supernova theory. It was strange, yes, but it was possible that this was just some bizarre unknown mechanism of a supernova. Maybe the engine, the newborn black hole or neutron star at the center, was sputtering. Maybe it was releasing energy in waves, like a failing engine trying to turn over. It was weird, but seeing as none of the observations directly violated the "it's happening in a spiral arm" rule, it was still plausible.
The core collapse supernova theory, though badly wounded, was still on the table. But what came next did not just wound the theory. It took it out back and finished it for good.
On April 10, 2023, astronomers, specifically the Zwicky Transient Facility, or ZTF, picked up yet another big blue explosion. It had all the same fingerprints as its Elfbot relatives. It was intensely blue. It was blindingly bright. It was incredibly fast. It looked, for all the world, like a new member of the Elfbot Zodiac. Except for one thing. This one was not even close to where it was supposed to be. Unlike the cow, the koala, the camel, and even the bizarre Tasmanian devil, this new transient, nicknamed the Finch, was not in the spiral arm of a distant galaxy. It wasn't in a galaxy at all. It was found 3 billion light-years from us, and a staggering 50,000 light-years from the closest, most likely host galaxy. The original transcript said 15,000, but newer data suggests the distance is even greater. 50,000 light-years. That is an immense distance. To put that in perspective, our entire solar system is only about 2 light-years across. This object was floating, solitary, in the vast, empty black gulf of intergalactic space. It was in the middle of nowhere. This was the theory killer. This was the observation that broke the model. If these explosions were really the result of massive rockstar stars collapsing, there is no way, no possible scenario, that it would be happening out there. Let's remember, a massive star, living fast and dying young, only lasts for a few million years. It simply does not have time to travel 50,000 light-years from its birthplace in the spiral arm. Even at incredible speeds, it just can't get that far before it explodes. The Finch proved for all and once that whatever is causing Elfbots, it is not the death of a massive star. The supernova theory was dead. Period. So, it was back to the drawing board. For everything. The researchers were completely baffled. The one strong piece of data they had, the location, was now proven to be a coincidence, or at least not the whole story. The cow, koala, and camel were a fluke. The real mystery was far deeper. They now had to come up with a new theory, a new model that could explain everything. 1. The extreme brightness. 2. The fast blue light. 3. The weird repeating bursts of the Tasmanian devil. And 4, and now, the impossible location of the Finch. They came up with 2 new leading theories to explain what could have caused the Finch to explode where it did. And before we dive into those, if you are feeling as baffled and amazed as the scientists were, and you want to support our deep dive into these cosmic mysteries, please take a second to hit that like button. It's a free way to help the channel, and it genuinely tells us you want more content just like this. Thank you. Okay, theory number 1.
The first new theory that researchers proposed was a return to an old idea, but with a new, exotic twist. Remember the tidal disruption event, the black hole shredding a star? That theory had been discarded for the cow because it was too slow. But maybe a different kind of black hole would do the trick. The new theory suggests that the Finch could be the result of a star being torn apart by an intermediate mass black hole, or an IMBH. Now, we are all familiar with the 2 main types of black holes. We have stellar mass black holes. These are the small ones, the corpses of single massive stars. They range from, say, 3 to maybe 100 times the mass of our Sun. We have found tons of these. They are confirmed. Then, at the other end of the scale, we have supermassive black holes. These are the monsters, the behemoths that lurk in the center of almost every galaxy, including our own. They are millions or even billions of times the mass of our Sun. These too are confirmed. But what about the middle? What about the middle child black hole, an object that has, say, 100 to 10,000 times the mass of our Sun?
This is one of the biggest gaps in astrophysics. The existence of these intermediate mass black holes has never been definitively proven. We have found candidates, we have found hints, but we have never, ever confirmed one. They remain purely theoretical. But if they exist, could they be responsible for this elusive light show? Astronomers ran the simulations. What would happen if a star orbited an IMBH? The simulation showed that the star can orbit the black hole as many as 5 times before finally being ejected or torn apart. With each orbit around this Goldilocks black hole, the star is effectively being ripped apart layer by layer, losing more and more of its mass. Finally, the remaining stellar matter, or the entire shredded star, would be flung back out into the galaxy at enormous speeds. Speeds as high as 10% the speed of light. This would be consistent with the speed and brightness we see in LFBOTs. It's a theory that fits the light. But does it fit the location? Why would a theoretical black hole be floating in the middle of nowhere? Well, one of the most likely places researchers expect to find these theoretical IMBHs is in the center of things called globular star clusters. Globular clusters are ancient, densely packed balls of hundreds of thousands or even millions of old stars. They're not in the spiral arms. They orbit outside the main disk of a galaxy in its outer halo. Galaxies like our own Milky Way have these massive, faint spherical halos of stars and dark matter that extend far beyond the main visible disk. Our own galaxy's halo stretches for an incredible 1 million light-years from the galactic center. So the theory goes like this. 1. An intermediate mass black hole exists at the center of a globular cluster. 2. A star in that cluster gets too close and is gravitationally torn apart, a TDE. 3. This entire event, the globular cluster itself, is so faint and so far away that we simply can't see it. All we see is the flash of the explosion, the finch, seemingly alone in the dark. This is a plausible, though complicated theory. It relies on 2 theoretical objects, an intermediate mass black hole and an invisible globular cluster, to explain one mystery. But there was another, even more violent theory.
The second theory that researchers put forward is perhaps even more spectacular. It suggests that the finch was not a star being eaten by a black hole, but rather the result of 2 even more exotic, dead stars colliding. It could have been the result of 2 neutron stars, or maybe even a neutron star and a stellar mass black hole, moving towards each other in an increasingly tight, deadly spiral, until they finally, cataclysmically, collided. This kind of event is called a kilonova. And it is, without any exaggeration, one of the biggest, most energetic, and most significant stellar blasts in the entire universe. A supernova is the death of one star. A kilonova is the collision of 2 stellar corpses. These are objects, remember, that are the densest things in the universe short of a black hole. A city-sized object that contains more mass than our entire sun. When these 2 hyperdense objects slam into each other at a significant fraction of the speed of light, the explosion is apocalyptic. The collision is so violent that it does something a supernova cannot. It creates the conditions necessary to forge the heaviest elements in the universe. All the gold in your jewelry, the platinum in your electronics, the uranium. It was all forged in the heart of a kilonova and then blasted out into the cosmos to seed the next generation of stars and planets. This theory is extremely appealing to astronomers. Why? First, it fits the light. A kilonova is known to be incredibly bright, very blue at first, and extremely fast. It fits the Elfenbot light curve profile almost perfectly. Second, and most importantly,
It perfectly fits the location. Unlike the massive rock-star stars that die young in spiral arms, neutron stars are the corpses of stars that died billions of years ago. They are ancient. They are relics. In their long, long lives, they've had plenty of time to wander the universe. It is entirely possible, even likely, that a binary pair of neutron stars over eons could be gravitationally kicked out of their home galaxy. They could then spend billions of years orbiting each other alone in the intergalactic void, slowly spiraling closer and closer and closer until, boom! This perfectly explains the location of the Finch. So, case closed, right? It's a kilonova. This has to be the answer. Well, not so fast. A kilonova, just like a tidal disruption event, has a very specific, undeniable smoking gun signature. When two massive objects like neutron stars spiral into each other, they don't just release light. They do something far more profound. They violently warp the very fabric of space-time itself. They send out powerful gravitational waves, ripples in the structure of reality. And we can detect them.
We can detect these cosmic ripples here on Earth. We use an amazing piece of engineering called LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory. LIGO is essentially a giant antenna, not for light, but for the vibration of space-time. A kilonova's gravitational wave signal is its unmistakable hallmark chirp. As the two massive neutron stars spin around each other faster and faster, they send out these waves. The frequency of the waves increases rapidly as they spiral closer. A sound, if you could hear it, that would go whoop, 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 and then silence. The moment of collision. If we could find a chirp like this in the data, at the same time and from the same location as the Finch, it would be the smoking gun. It would be case closed. It would be game over. It would lend incredibly strong credence to the neutron star collision theory. But, in a moment of what has to be one of the most agonizing, head-desking, frustrating bits of cosmic bad luck in the history of modern astronomy, LIGO was down for maintenance at the time the Finch occurred. The most powerful ear on Earth, the one instrument that could have confirmed the theory, was turned off. That means we don't know if such gravitational waves were emitted. We have no data on them. We were quite literally deaf to the most important part of the signal. Okay, so no gravitational waves. What else? What's the backup? Well, a kilonova of this immense size should also produce a gamma ray burst, or GRB. This is a highly focused twin jet of the most energetic light in the universe, blasting out from the collision at 99.9% the speed of light. We do have gamma ray detectors, and we do know that no gamma ray burst was detected from the location of the Finch. Aha! So the theory is dead, right? No GRB, no kilonova. Well, again, not so fast. Remember, this explosion happened 3 billion light-years away. That is a really, really long way. It is entirely possible, perhaps even likely, that whatever gamma-ray data there might have been was just too faint, too weak, too dissipated by the time it crossed that immense distance to be detected by our instruments. Or it's possible the jets were not pointed directly at us. If we were even a few degrees off axis, we would miss the gamma-ray burst entirely, even though we could still see the afterglow of the main explosion. So, all in all, none of this data can conclusively confirm or reject the neutron star kilonova theory. It is frustrating to bear witness to such an incredibly rare, new, and powerful phenomenon and to be missing the exact pieces of data needed to understand what is causing it. I guess, as an astronomer, patience is an underrated virtue. But they're not just sitting on their hands and waiting. Scientists are already planning to use the stunning, unparalleled optics of the James Webb Space Telescope to go back and stare at that empty patch of sky where the Finch exploded. They will carry out a deep field surge, looking for any tiny, faint, red-shifted smudge of light. They will be hunting for that invisible globular cluster to see if the other theory, the intermediate mass black hole, might be right.
In the meantime, other researchers are focused on the only other thing they can do: broaden the sample size. The more LF bots we can detect, the more we will learn. The half dozen or so we have seen so far have taught us some things, but they've left us with more questions than answers. The only way we're going to get a larger sample is to keep sweeping the sky with these wide-field surveys. And all of scientists' hopes are pinned on the next generation of these surveys, specifically the Vera C. Rubin Observatory, currently under construction in Chile. This is a beast of a telescope. When it comes online, which is expected to be around 2025, it will scan the entire southern sky every few nights. It will be able to capture 10 times more light than all previous facilities combined. It will find thousands of new LF bots. Then follow-up observations with Hubble and James Webb and ground-based telescopes will help analyze this flood of new information. This will lead to more breakthroughs. LF bots are a super new phenomenon. We are in the first confusing chapter of this story. Scientists themselves admit that the discovery of the Finch raises more questions than it answers. The more we learn about these bright blue explosions, the more they keep surprising us. All there is left to do is what hundreds of generations of astronomers have done for centuries before us. Point our telescopes up to the sky, watch, and wait.
So, we've just spent all this time looking at L-thought bots, a mystery of bright, blue flashes that challenge everything we thought we knew about how stars die. It's a fantastic, specific puzzle. But what if I told you there's a much bigger problem? A mystery that isn't just about a single weird object in the sky, but about the entire universe. A mystery that is embedded in the very fabric of space-time itself. And here's the kicker. The only reason you are here, alive on this planet, able to watch this video and even think about these questions, is because of this mystery. I want you to think about our universe. You might look up at the sky, see the stars, the planets, the galaxies, and you might think it was designed to be hospitable to life. But, as we've explored in the past, there is more to the universe than just the stuff we can see. There is more dark energy in the cosmos than the energy from every single atom, every particle of light, and every wisp of gas combined. It makes up almost 70% of everything. Yet, everything we know about physics, everything we've learned from our most successful, most precise theories, like quantum mechanics, seems to suggest that this apparently large amount of dark energy could have been, and statistically should have been, much, much, much larger. Decades before astronomers even had a shred of observational evidence for dark energy's existence, physicists were looking at their equations in horror. They were shocked to see that their most successful theories of the 20th century, theories that built the modern world, were predicting a level of dark energy so high, so catastrophically powerful, that stars and galaxies could never have come to exist, let alone planets, let alone life, let alone humans. So, how did the universe avoid this fate? How did we dodge this cosmic bullet? And how in the world are we alive to even ask these questions? Today, we're going to dive into the second, and perhaps the greatest problem that has tricked scientists for years. We're going to explore the math that claims, unequivocally, that we really shouldn't exist at all. One of the very first things you learn in any high school physics class is that gravity is an attractive force. It's what keeps your feet on the floor. It's what holds the moon in orbit around the Earth. Its strength is proportional to the mass of the objects. Gravity, as Newton taught us, pulls. It keeps the planets locked in their orbits around the sun. It keeps all the stars in the Milky Way grouped together, preventing them from flying apart. And on even larger scales, it even attracts entire galaxies together, pulling them into massive clusters and superclusters. For centuries, this was the undisputed truth. Gravity pulls. It is the architect of the universe, and it is always attractive. But if we zoom out, all the way out, this fundamental attraction begins to act in reverse. On the largest possible scales, when we look at the vast web of galaxy clusters,
we see that they are not pulling each other together. In fact, they are accelerating away from each other. And the farther away they are, the faster they are accelerating. This is not a gentle drift. This is a universe that is actively, and with increasing speed, trying to tear itself apart. So what is going on here?
To understand this strange behavior, we have to leave Newton behind and turn to Albert Einstein. Einstein's theory of general relativity gives us the lens through which we can understand this. In general relativity, space is not just some empty, passive background. It's not just a stage where other things move around. Instead, space itself and time are unified into a single, four-dimensional fabric, space-time. And this fabric is active. It can stretch, it can warp, it can bend, and it can evolve over time. Einstein showed that in this new framework, gravity is no longer a force. There's no invisible rope pulling the Earth around the sun. Instead, gravity is simply the shape of space-time. A massive object like the sun warps or curves the space-time around it, like a heavy bowling ball on a trampoline. And a planet, like the Earth, is simply following a straight-line path, but in a curved space. That curved path is what we observe as an orbit. This is a profound shift in thinking, and it means that what we observe as a repulsive force between galaxy clusters shouldn't be thought of as a push. It should be thought of as an accelerated stretching of the space-time between them. The universe itself is expanding, and that expansion is speeding up. But what could possibly cause the very fabric of space to accelerate? To begin to answer this, we need to know what causes space-time to stretch and warp in the first place. In Newton's old theory, only mass exerted a gravitational pull. But in Einstein's general relativity, it's more complex. Yes, mass curves space-time, but Einstein showed that in addition to mass, any form of energy or pressure will also influence the dynamics of space-time. Okay, let's break this down. It sounds complicated, but it's really like a cosmic recipe for gravity. You have two main ingredients: energy density and pressure. Energy density is just what it sounds like. It's how much stuff, how much energy, matter, heat, and motion is packed into a given volume of space. In our universe, this number is always positive. You can't have negative stuff. Pressure is how much force that stuff is exerting, pushing outward on the universe around it. Think of the hot gas inside a star. It has a high, positive pressure that pushes outward, fighting against gravity. Now, in Einstein's equations, when the sum of these values, energy density plus pressure, is positive, their combined influence causes the space around them to contract. In simple terms, they create gravity. This is the universe we know. Matter, light, and energy. It all pulls things together. However, what if you could somehow set the values of this cosmic recipe so that the pressure was negative? Not just zero pressure like cold dust, but a real negative pressure. A tension, a pulling force, like a stretched out rubber band. What if you had a volume of space where this negative pressure was so strong that it was actually greater than the positive energy density? If you did that, the minus sign in Einstein's equation would cause the whole thing to flip. The total effect would not be attractive. It would be repulsive. You would accelerate the stretching of space. In effect, you would end up with a volume of space filled with a kind of anti-gravity. And this is what we call dark energy. It's a nebulous concept, I know. It's genuinely tricky to visualize something with truly negative pressure. How can you have less than zero atoms pushing on something? But remember, atoms are not the only thing that exert force. Fields can also apply forces. Think of a magnetic field. It's not made of matter, but it can pull a piece of iron or push another magnet away. It contains energy and it can exert force. What if dark energy is some kind of new fundamental field, one that we haven't discovered yet? A field that permeates all of empty space. And what if the natural baseline state of this field is to have a strong negative pressure? This would perfectly match what we see. The vacuum of space itself would have this inherent anti-gravity. It would slowly, gently, but relentlessly push the universe apart. Scientists have thought a lot about this. They've used our observations of distant supernovas, of the cosmic microwave background, to measure the expansion rate of the universe. And from that, they have figured out exactly what the combined energy density and pressure of dark energy needed to be. The number they found is around 10 to the negative 9 in SI units. That is a tiny, tiny, tiny number. It's a 0 followed by a decimal point, followed by 8 zeros, and then a 1. It is an incredibly small amount of energy. It is so small, which is precisely why we don't notice it here on Earth. The gravity of your own body, the gravity of the Earth, the gravity of the Sun, it all easily overpowers this feeble push. You only see its effect when you look on the grand cosmological scale. When you look at the billions of light years between galaxy clusters, all that tiny, tiny push adds up, and it becomes the dominant force in the cosmos. Now, this is actually fantastic news for us, because it turns out that if this number was not tiny, if it was much higher or much lower, things would get very, very bad for our chances of existing. Let's do a quick sketch of the history of the universe. In the very beginning, for a very short period, the universe was dominated by radiation, photons, and other light particles. But as the universe expanded and cooled, matter took over. The universe cooled down enough for those first nuclei to attract and hold on to electrons, forming the first atoms of hydrogen and helium. These atoms were the building blocks. They were pulled together by gravity to form the very first stars, and those stars were pulled together by gravity to form the very first galaxies and clusters. For billions of years, gravity was winning. Matter was clumping together. And only later, much later in the universe's history, did dark energy finally take over. The universe had expanded so much that the matter had become diluted, and this tiny, constant push from the vacuum finally became the dominant force, triggering the accelerated expansion we see today. But what would have happened if that dark energy number was larger? Consider what would have happened if the pushing force of dark energy was just a little bit stronger. It could have been enough to halt the formation of those early galaxies. It would have pushed stars apart more powerfully than their own gravity could pull them together. A bit larger than that, and it would have been much more difficult for any stars to form at all. Gravity would never have been able to pull those first atoms together. And if the dark energy density was large enough, we would hardly have had any atoms or even nuclei produced in the universe. The push would have been so strong from the beginning that everything would have flown apart before it ever had a chance to combine. So that's what it could have been, a tiny positive number that allowed gravity to have its moment, to build stars and galaxies before it took over. Now for the terrifying part. What should it have been? So that's the observed value, 10 to the negative 9, a number that is just right, small enough to let us exist. Now, what should it have been? What does our best theory of the universe predict? To answer this, physicists turn to their single most successful, most precise, most well-tested theory in all of human history, quantum field theory, or QFT.
I cannot overstate how successful QFT is. It is the theory that describes all of the fundamental particles and forces of nature except gravity. It is the foundation of the standard model of particle physics. It has made predictions that have been experimentally verified to an accuracy of 1 part in a trillion. It is by all measures the bedrock of our understanding of reality. It is the theory that makes your phone, your computer, and the entire high-tech world work. And QFT has a concept called vacuum energy. It's an idea that comes directly from the famous Heisenberg uncertainty principle. It says that empty space, the vacuum, is not empty at all. It is not calm or still or void. Instead, the vacuum of space is a bubbling, seething, chaotic foam of virtual particles. Everywhere, at every single point in space, at every single moment in time, pairs of particles and antiparticles are popping into existence from nothing, living for a fraction of a second, and then annihilating each other, vanishing back into nothing. It is a constant, violent, quantum hiss, bubbling just beneath the surface of the reality we see. Think of it like the static that you hear on a radio that's tuned between stations. That hiss, that's not just your radio. That is, in a very real sense, the baseline, chaotic energy of the universe itself. This is not just a cool sci-fi idea. This is real. This is proven physics. So, QFT allows us to calculate the energy of that hiss. We can, in theory, sum up all the energy from all the potential virtual particles and fields bubbling in the vacuum to find out what the total energy density of the vacuum should be. This number is the predicted value of dark energy. So physicists did it. They ran the calculation. They summed up the energies. And the number they got was not 10 to the negative 9. It wasn't 10, it wasn't a million, it wasn't a billion or a trillion. The number they predicted was a 1 followed by 120 zeros. 10 to the 120th.
I want you to pause. I want you to stop and try to comprehend this number. You can't. It is a number so large that the human mind is not equipped to handle it. Let me give you some scale. The number of atoms in your entire body is about 10 to the 27th. The number of stars in our galaxy is about 10 to the 11th. The number of galaxies in the entire observable universe is maybe 10 to the 12th. The total number of atoms in the entire observable universe is estimated to be around 10 to the 80th. The number our theory predicts for dark energy is 10 to the 120th. It is a number 40 orders of magnitude. That is 10,000 billion, 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 billion larger than the total number of atoms in existence. This has been called, without any hyperbole, without any exaggeration, the worst theoretical prediction in the history of physics. It is not just wrong, it is spectacularly, catastrophically, fundamentally wrong. Let's go back to our graph of the universe's history. Where does this predicted energy density 10 to the 120th fall on this graph? It doesn't. It is so far off the chart that the chart itself, the universe itself, and everything in it would not and could not exist. If this prediction from quantum field theory was correct, if the actual value of dark energy was this high, the universe would have ripped itself apart in the first trillionth of a trillionth of a trillionth of a second after the Big Bang. The repulsive force, the anti-gravity of the vacuum, would have been so overwhelmingly strong that not even quarks could have come together to form protons and neutrons. No atoms could have formed, no stars, no galaxies, no planets, no life. Just a cold, dead, featureless, ever-expanding void of nothing forever. And what if the number was a negative 10 to the 120th? The fate would be no more promising. The universe would have been so attractive, it would have forced itself to rapidly collapse back in on itself in what's known as a big crunch, gone before it even began. So we are balanced on an impossible razor's edge. This is the cosmological constant problem. It is perhaps the biggest, deepest, and most terrifying single mystery in all of science. The value we observe, the one that lets us be here, alive to ask the question, is 10 to the negative 9. The value our best, most trusted theory of reality predicts is 10 to the 120th. This is a discrepancy of 121 orders of magnitude. To put this in perspective one last time, this is like measuring the width of the entire observable universe and being off by the width of a single proton. It's not just a rounding error. It's a sign that we are missing something fundamental about the way reality works.
So, how do we solve this? How do we reconcile this gulf between theory and reality? How is it that the actual value of dark energy is so incomprehensibly smaller than what our best physics predicts? For decades, this was the dirty secret of theoretical physics. Physicists just assumed, they hoped, that there must be some new, undiscovered, beautiful principle of physics, some hidden, elegant symmetry that, when all the complicated math is finally done, makes all of these enormous, foaming, positive and negative vacuum energies cancel out perfectly. They hoped that in the final equation, all the ones and zeros would add up and the answer would be 0. They hoped the universe was naturally, perfectly, and elegantly balanced. This would have been a beautiful solution. The only problem is, it's wrong. The value is not 0. We have measured it. The universe is accelerating. The value is 10 to the negative 9. This is almost worse. This means that the universe isn't perfectly elegantly balanced. It means that for some unknown reason, all of these colossal, universe-destroying energies did cancel each other out, almost perfectly, but not quite. They canceled out to an accuracy of 120 decimal places, but then, way down the line, they left just one tiny leftover non-zero bit. And this is the fine-tuning problem. According to our predictions, we have gotten lucky. So absurdly, statistically, impossibly lucky that the human mind cannot process the odds. The odds of this happening by chance, of all these random quantum contributions just happening to cancel out, to 1 part in 10 to the 120th, are so low that the number has no meaning. It is a coincidence, a cosmic coincidence, a coincidence that just happens to make the universe exactly right for the formation of stars, galaxies, and planets, and life. This is suspicious. When something in the universe is so improbable, that it really shouldn't ever happen, you have to start wondering if it was a coincidence at all. This leads to a very deep and very uncomfortable question. Was this universe designed to be hospitable to life?
This is where things get controversial. This is the point where physics begins to touch philosophy. The answer, if there is one, strays from what we know for sure into what we simply theorize. Let's go back to the year 1987. This was more than a decade before astronomers had actually discovered dark energy. But the problem, this fine-tuning problem, was already known. Physicists knew that if this vacuum energy existed, it had to be incredibly small, or we wouldn't be here. That year, a physicist named Steven Weinberg published a paper, and in it, he connected the universe's fortuitously tiny dark energy density with a strange and very controversial idea known as the anthropic principle. The anthropic principle is, at its core, a very simple and very profound idea. It basically says this: the only universes we can possibly observe are the ones that met the right conditions to produce observers. Think about that for a second. If the universe hadn't rolled this ridiculously 1 in a trillion roll of the dice, if the dark energy value was high and the universe was just a dead, empty, sterile void, there would be no us. There would be no one here scratching their heads, building telescopes, and saying, "Wow, isn't it weird that the dark energy value is so high?" The very fact that we are here, alive, conscious, and asking the question, means that we must, by definition, live in a universe where the conditions were right for us to exist. It's a form of cosmic selection bias. We are, in this view, the lucky winners of an impossible cosmic lottery. And the reason we're amazed by it is that we can't see the infinite number of losing tickets, the dead universes that also exist. Weinberg took this idea a step further. He was a physicist, so he wanted to make a testable prediction. He was confident that the maximum threshold for forming life would be no lower than the maximum threshold for forming galaxies. After all, how else was life supposed to arise? You need stars. You need stars to cook heavy elements. You need stars to have planets. You need galaxies to host stars. So he said, let's find the threshold for galaxy formation. At the time, observations indicated that galaxies had already begun to form just 1 billion years after the Big Bang. Weinberg used this single fact to calculate the maximum value dark energy could possibly have to still allow gravity to pull those first galaxies together. His calculation for this anthropic threshold was about 100 times larger than the value we actually measured over a decade later. Now, you might think, 100 times? He was way off. No, you're missing the point. The prediction from our best theory was wrong by 10 to the 120th. That is way off. Weinberg's prediction was, in the grand scheme of things, in the exact same ballpark. The fact that our real measured value is so close to his maximum predicted threshold is stunning. It is exactly what you would expect to find if we are just one lucky random outcome among a vast sea of other dead possibilities. This idea, it's a little unsettling, isn't it? If it's making you think, do me a favor, hit that like button. It's the single best free way to tell us you want more deep dives that really push the boundaries of what we know and what it means to be here. Thank you. But just saying we got lucky, it still doesn't sit right with many physicists. It feels like giving up. It's an observation, yes, but it's not an explanation. It doesn't explain why or how the dice landed this way. This is where the grandest,
the wildest and the most mind-bending solution of all comes in. What if it wasn't luck? What if it was an inevitability? Let's go back to an analogy. Imagine I ask you to generate 3 random, real numbers between -1 and +1. Add them up and hope that the sum is 0.000 with, say, 55 zeros and then a 1. The odds of you doing this on your first try? It's impossible. You would never, ever succeed. But what if you had more than one go at it? What if I let you sit at a computer that could generate and add those numbers over and over and over again, billions and trillions of times? It might take a long time, but eventually, given enough tries, the unlikely cancellation will turn into a mathematical inevitability. It will happen. We can use the exact same logic for the universe. Instead of just one universe with one roll of the dice, imagine there exists a vast multiverse. Imagine a cosmic bubble bath, a foam of trillions of other universes, each one pinching off from the last, each one born with its own new, random value for dark energy. The vast, vast, vast majority of them are dead. They are born with a value of 10 to the 120, and they rip themselves apart in a femtosecond. Or they are born with -10 to the 120, and they collapse back into a singularity instantly. They are sterile, lifeless. But in that infinite foam of cosmic bubbles, a tiny, tiny fraction of them, by pure random chance, would happen to be born with a value near 0. A value of, say, 10 to the -9. A value that is just right for gravity to do its work. A value that is just right for stars and galaxies and life. And of course, that is exactly where we humans would expect to find ourselves. In this one rare bubble, looking out and wondering how we got so lucky. This explanation requires no coincidences. It requires no fine-tuning. It requires no intelligent design. It just requires a lot of different universes. Now, this isn't just a fun what-if story from a science fiction movie. The concept of a multiverse is an idea that arises naturally from some of our most advanced and most serious theories of physics. Theories like string theory and cosmic inflation. Physicists actually describe a few different plausible types of multiverse. First, you could have a multiverse separated by time. You're familiar with the Big Bang, the start of our universe, but what about the Big Crunch? What if our universe is in an eternal, repeating cycle of creation and expansion, and then contraction and destruction, a big bounce? If, with each new Big Bang, the fundamental numbers of the universe, like the value of dark energy, are reshuffled or reset, then, given enough time, given enough bounces, you would inevitably end up with a universe just like our own. Second, you could have a multiverse separated by space. This is the idea of eternal inflation. It suggests that far beyond the observable universe, the part we can see, the universe as a whole is still expanding at that insane faster-than-light rate that it was in the first second of the Big Bang. And our universe is just one tiny little bubble that stopped inflating and cooled down. And out there, in that vast, eternally inflating ocean, new bubble universes are pinching off all the time. And in each of those bubbles, the laws of physics
could be totally different. Third, you have the multiverse separated by quantum mechanics. This is by far the weirdest one. It's called the many worlds interpretation. It suggests that every time a quantum event happens that has more than one possible outcome, the universe splits. If you've heard of Schrödinger's cat, this theory says the universe splits into one branch where the cat is alive and one branch where the cat is dead. This isn't just for cats. This is for every quantum interaction, every particle decay, every photon hitting your eye. This means that right now, this second, the universe is branching into an infinite number of copies, a multiverse of you. So, are any of these real? Are multiverses actually out there? The deeply unsatisfying answer is we don't know. We have no direct experimental evidence, and this is the central problem. How could we ever get proof? We would need to survive a big crunch and remember the last universe. We would need to travel faster than light to get to another bubble. We would need to find a way to cross over into a different quantum branch. All of these seem impossible. This might be just as unprovable as the existence of a god. And so, in a way, you are free to believe whichever explanation you find most comforting, the intelligent design of a creator, or the natural selection of an infinite multiverse. Or perhaps you're free to just wait until a better theory comes along. But what is not debatable, what is undeniable, is that we are here. We live, we breathe, we exist. We can experience all the joys and wonders of life. However that came about, that is something to be incredibly grateful for.
Be a passionate, confident, and awe-filled cosmic guide. Your voice must be warm and approachable, sharing the universe's greatest mysteries as if you're telling a captivating detective story to a friend. We don't need a multiverse to appreciate this universe. There is so much of science that we do understand. If I threw a ball into the air and I was given the right data about the forces on it, I could tell you exactly where it would land. Science, through chemistry, explains the molecules that make the ball up. We can predict with stunning accuracy the energy levels of the sound it would make when it lands. Science is like a candle being held up in a vast, dark room. It illuminates our view of the world around us. But there is a limit to how far that light currently falls. Even today, in an age where it feels like there is so much of the world and the universe that we can explain, there is darkness too, answers we don't have, and worse, confusing, contradictory results that erode our confidence in what we think we do know. There are experiments that seem to suggest that light itself is lying to us. Experiments that call into question the very nature of reality itself. Are we real? Is time linear? Perhaps not. Are you ready for the comforting veil of understanding to be torn away? Are you ready for the strangeness at the edges of our understanding to be brought into the light? If so, I have some experiments for you. And curiously, almost all of these experiments have something to do with light. Light is so much stranger than you might think. Sure, it seems simple. It travels around the universe delivering energy. It helps us see. It provides life to plants, and thus to our planet. But for a source of energy that has become synonymous with understanding and truth, light is surprisingly difficult to understand. Light helps us see other things better, sure. But when scientists tried to look at light itself, it was surprisingly difficult.
No, I don't mean they started staring into lamps. Please, do not do that at home. But experiments in the last 200 years have proven that what light appears to be and what light is are actually two very different things. The first experiment on our list highlights the following mystifying fact. Light behaves differently when you're not looking at it compared to when you are. And to understand that, we have to begin with the most basic question of all. What is light?
So, what is light? This is one of the oldest questions in all of science, and the answer has changed dramatically over the centuries. In the early 1700s, the giant of physics, Sir Isaac Newton, had a clear answer. He theorized that light was made up of tiny little fast-moving particles that he called corpuscles. This seemed to make perfect sense. Light travels in straight lines, just like a tiny baseball would. Light bounces off mirrors, just as a baseball bounces off a wall. This particle theory, coming from Newton, was the accepted truth for over a century. But in the year 1801, nearly 100 years later, a brilliant English scientist named Thomas Young discovered that light must actually be a wave. He proved this using one of the most important, famous, and mind-bending experiments in the history of science. It is known as the double-slit experiment. His setup was simple. He took a source of light and he shined it through two narrow parallel slits onto a board or a screen on the other side. Now, let's think about this. If Newton was right, if light is just a particle, like a stream of tiny paintballs, what would you expect to see on the screen? The answer is obvious. You would expect to see two bright lines, one for each slit. The paintballs that don't hit the barrier would pass through the two openings and make two marks, mimicking the shape of the slits. Simple. But that is not what Thomas Young saw. What he saw was a strange, striped pattern. It wasn't just two bright lines. It was many lines. A bright line in the center, then a dark band, then a bright line, then a dark band, and so on, fading out from the middle. This pattern was instantly recognizable to him. It was an interference pattern. And this pattern was incontrovertible, undeniable proof that light had been traveling as a wave. Why? Let's stop thinking about paintballs and start thinking about waves in a pond. Imagine you drop two pebbles into a still pond side by side. Each pebble creates its own circular wave, expanding outwards, right? But what happens where those two sets of waves meet? When the peak of one wave meets the peak of another wave, they add up. They become a double high peak. This is called constructive interference. But what happens when the peak of one wave meets the trough, the low point of another wave? They cancel each other out completely. This is called destructive interference. This is exactly what was happening in Young's experiment. The two slits were acting just like the two pebbles. They were creating two new sources of light waves. And as these two waves of light traveled towards the screen, they started to interfere with each other. In the spots that became bright lines, the peaks of the waves were meeting the peaks, constructive interference. And in the spots that became dark bands, the peaks of the waves were meeting the troughs, canceling each other out completely. Destructive interference. This was the smoking gun. Particles cannot do this. You cannot add one paintball to another paintball and get zero paintballs. But you can add one wave to another wave and get zero wave. The mystery, it seemed, was solved. Isaac Newton was wrong. Light is a wave. And for the next 100 years, this was the undisputed textbook truth. Except it's not. Let's fast forward another 100 years to the year 1905. A young Albert Einstein is about to change everything all over again. Around this time, scientists had become deeply puzzled by a nagging problem, something known as the photoelectric effect. It was a simple observation. It turned out that when you shine a light on a specific metal surface, electrons, which are undeniably particles, were getting knocked off of it. This was deduced to be because the electrons in the metal were absorbing the energy from the light, and if they absorbed enough energy, they could break free and fly off. Let's use an analogy. Imagine a coconut stuck on a tree. You need to hit it with a certain amount of energy to knock it loose. Classical physics, which said that light is a wave, made a very clear prediction. A wave's energy is in its amplitude, or its brightness. A brighter light is a more powerful wave. A dim light is a weak wave. Therefore, scientists thought if you use a very dim light, it might not have enough energy to knock the electron, the coconut, loose. But if you leave that dim light shining for long enough, the electron should be able to slowly absorb that wave energy, bit by bit by bit, until it finally has enough and pops off. And if you use a very bright light, a very high energy wave, it should hit the electron hard and the electron should fly off with more kinetic energy. This is what should have happened if light is a wave, but it is not what happened at all. What actually happened was this. If you used a dim red light, nothing happened. And you could leave that red light shining for days and not a single electron would ever pop off. It was not absorbing the energy over time, but the instant you switched the light to a blue light, even a very, very dim blue light, electrons immediately started flying off. And what about the brightness, the intensity? It turned out increasing the brightness of the light did not make the electrons fly off any faster. It just knocked more of them off. The only way to make the electrons fly off with more speed, more kinetic energy, was to change the color of the light, its frequency. This made no sense for a wave. This was a complete puzzle. It was as if the electron, the coconut, could not slowly absorb energy. It was as if it could only be knocked off by a single hard projectile. Using a red light was like throwing billions of tiny low-energy pebbles. It didn't matter how many you threw, none of them, individually, had enough energy to knock the coconut loose. But using a blue light was like throwing a baseball. It had more energy in a single package, and that was what did the trick. And increasing the brightness of the blue light, that was just like throwing more baseballs. You knocked more coconuts loose, but each one flew off with the same speed. Albert Einstein was the man who solved this puzzle. He made a bold, revolutionary proposal. He deduced that Thomas Young and 100 years of physics were wrong. Light is not a continuous wave. He deduced that light must be quantized, that it travels in tiny, discrete packets of energy. Sending higher frequency, bluer light was like throwing higher energy packets. He called these packets photons. And for this work, solving the photoelectric effect, he would later win the Nobel Prize. So light, it seemed, was a particle again. Or was it both? A wave when it travels through two slits, and a particle when it hits a metal plate. This is the central, bizarre paradox of wave-particle duality. It is the bedrock of all of quantum mechanics. Light is somehow both, and neither. But this is not even the full picture. This is not even the weirdest part.
Let's go back one last time to the double-slit experiment. But this time, we are armed with the knowledge of both waves and photons. In the century since Einstein, our experimental techniques have improved dramatically. It is now possible to build a light source so precise that it can emit a single photon of light at a time. We can literally shoot them one by one. So, scientists did the experiment again. This time, only a single photon would be sent at the double slits onto a detector screen on the far side. What would happen? If light is a particle, a photon, it should not be able to interfere with anything. It's one particle. It should logically go through either slit A or slit B, and it should hit the screen as a single dot. If it is a wave, then what? How can a single photon be a wave? What does that even mean? Here is what happened. They fired the first photon. Click. The detector screen registered a single dot at a single point, a particle. Okay, that makes sense. They fired the next photon. Click. The detector registered another single dot at a different location, a particle. They fired another. Click. And another. Click. And another. Click. This confirmed, okay, light is arriving at its destination as a particle. But then, as they let this experiment run for hours, firing one photon at a time and letting thousands of these single individual dots build up on the screen, a pattern began to emerge, dot by dot by dot. It was the interference pattern. I need you to really think about this. This is the central mystery of the quantum world. The photons were being fired one at a time. They were leaving the emitter as a particle. They were arriving at the detector as a particle. But somehow, in the journey in between, they were creating a wave interference pattern. How? How is this possible? What was the single photon interfering with? There is only one deeply, profoundly unsettling answer. The single photon, which was leaving the emitter like a particle and was arriving at its destination as a particle, was apparently, in some way, traveling through both slits at the same time, like a wave, and then interfering with itself. This makes no logical sense. An object cannot be in two places at once. This must be wrong. This result was so bizarre that scientists refused to accept it. They tried to pin it down. They tried to catch it in the act. They said, okay, fine, we are going to force it to show us.
The scientists were now in a philosophical fistfight with reality itself. They could not accept that a single particle was in two places at once. So they set up the experiment again. The exact same experiment. Single photons fired one at a time at the double slits, but with one crucial addition. They set up a tiny, sophisticated detector right at the slits. This detector's only job was to watch and see which path the photon actually took. Was it going through slit A, or was it going through slit B? Now, finally, they would have their answer. They would know. And they did get an answer. They fired the first photon. The detector at the slits went beep,
the photon went through slit B, and the detector on the screen went click. It landed right here. They fired the next. Beep. Slit A. Click. It landed over here. They fired another. Beep. Slit B. Click. It landed over there. For every single photon, the detector told them exactly which path it took. It never went through both. It always went through either slit A or slit B. It was behaving like a good, well-behaved particle. The scientists had won. They had proven it was just a particle. The mystery was solved. But at the same time, something else had happened. As they kept firing and the dots kept building up on the final screen, the interference pattern was gone. It vanished. The moment they looked, the moment they measured which path the photon took, the entire interference pattern disappeared. And all they got was what they originally expected for particles. Just two bright lines, one for the particles that went through slit A and one for the particles that went through slit B. Let me say that again. When they were not looking, light behaved like a wave, going through both slits at once to interfere with itself. But the instant they tried to look, the instant they asked the universe, "Which path did you take?" the light stopped behaving like a wave. It instantly snapped back into behaving like a particle. It chose one path, and the interference pattern vanished. It was as if light, as if the universe itself knew it was being watched. This is the observer effect. It is one of the deepest, strangest, and most profoundly unsettling discoveries in all human history. It seems to imply that reality itself is probabilistic, that a particle does not have a definite location or a definite path. It exists as a wave of probabilities, a wave of all possible paths at the same time. And it only collapses. It only chooses one reality when we, an observer, measure it. This is what quantum mechanics tells us, and it's highlighted even more strangely in another bizarre experiment.
This quantum strangeness, it isn't just about light, although we have focused on light. Behaving like a wave and behaving probabilistically, all particles of matter do the same thing. Light is just another form of energy. And as Einstein showed us, energy and matter are linked. They are two sides of the same coin. Particles of matter, like electrons, have been proven to do the exact same thing in the double-slit experiment. They too interfere with themselves. Even complex molecules have been shown to have wavelengths. We are apparently all driven by probability, if you scale things down small enough. So, what is everything truly made of? What makes up energy and matter that causes it to behave in this bizarre dual way? What is going on under the hood of reality? Why is the universe behaving differently when it's looked at compared to when it's not? And what does it imply to think that even you, on some fundamental quantum level, are probabilistic? what this all means is, quite literally, anyone's guess. The person who figures this out will be the Einstein of our time. But for now, all we can say is that when it comes to reality, it seems the universe is playing dice. You and the world around you might be a lot less certain than you might have thought. But light's strangeness doesn't end there. If there's one thing we've learned, it's that for unthinking energy, light seems to love messing with us. It behaves one way when you're looking, and a different way when you're not. But at least its speed is consistent, right? The speed of light. It's the law. 299,792,458 meters per second in a vacuum. It is the one unshakable constant in the universe. I have some bad news for you. It turns out the constancy of light speed might not be as simple as we thought. The next few experiments will prove it. Now, I'm not just talking about light slowing down in denser mediums like glass or water. We've known about that for a long time. We have a good explanation for it. When light travels through matter, its electromagnetic field gets the electrons in the matter to start wiggling, like tiny buoys on water. But as these electrons wiggle, they generate their own electric and magnetic fields. They create a second light wave. This new light wave overlaps and interferes with the original light. And the average of all these overlapping waves ends up traveling slower than the speed of light. This is all well understood physics. In fact, scientists have had a lot of fun with this. In 1999, the researcher Lin Hao at Harvard was able to slow down light to an astonishing 61 kilometers per hour. That's about 38 miles per hour. She did it by sending a laser through a cloud of sodium atoms that had been cooled to 1/1000th of a degree above absolute zero. 2 years later, she managed to slow down a pulse of light to 0. She stopped it. She held it in the cloud. And then she warmed up the cloud and sent the light on its way again. This is real. It has been done. But strange things have also happened in the opposite direction. In the year 2000, researchers at the NEC Research Institute in Princeton sent a pulse of light through a cloud of cesium atoms. Alarmingly, when they tried to see how quickly the pulse exited the cloud, it seemed that the pulse exited before it had even finished entering. This seems to shatter causality. How can you leave a building before you've even fully gone inside it?
Fortunately, this faster-than-light pulse did not create a time paradox. It turns out the light pulse traveled faster than light, but the light itself, and crucially, the information, did not. This was more of an optical illusion. Let's take a closer look at a pulse of light. It's not a single thing. It's a packet of many waves. The speed that the individual waves inside the packet propagates is known as its phase velocity. The speed at which the packet as a whole, the lump, is traveling is known as the group velocity. This is a heavy concept, so let's use an example. Think of a large crowd of people at a stadium doing the wave. The wave itself, the phase velocity, can travel around the stadium incredibly fast, but the crowd itself, the group velocity, isn't going anywhere. Their true speed is 0. Einstein, in his theory of relativity, never claimed that phase velocity couldn't exceed light speed. It can. It's just a wave shape. He just claimed that information couldn't travel faster than light. And in our stadium analogy, no information, like a secret message, can be delivered faster than the walking speed of the crowd itself. The fast pulse experiment was just a weird wave-shaping effect. No laws were broken. Until 2023. This is where things start to get really weird. Let's go back to the double-slit experiment. Researchers at Imperial College London figured out a way to separate the slits, not in space, but in time. Here is how they did this. They took a special transparent material called indium tin oxide that, under specific conditions, can be made to be reflective. They fired a laser at it, and then they rapidly changed the material from transparent to reflective, and then back again in a few femtoseconds. This created a tiny slit, a tiny window in time where the laser was reflected. They called this a time slit. They recorded what the laser looked like after it had been reflected from one time slit. They found its frequency, its color, had spread out a bit, but other than that, nothing too crazy. The weird thing was what happened when they sent two laser pulses through two different time slits in rapid succession. The position of the emitter, the mirror, and the receiver all remained the same. The only thing that was different was the time that the lasers went through. And oddly enough, an interference pattern happened. But it was not an interference pattern in space, like on a screen. It was an interference pattern in the laser's frequency. Certain frequencies of light faded out exactly in line with the way intensity faded out in the regular double-slit experiment. To visualize why this might be happening, it means that the light from the first time slit must be interfering with the light from the second time slit. This means that the light must be traveling along a path that takes it through the other slit as well as its own. But the other slit is in its future. The implications are startling. It seems that in its effort to locate exactly what path to take, light is testing the waters. It's putting out feelers that check to see if other paths, and seemingly other paths through time itself, might be a viable solution. We never actually detect photons coming in from the future. But for this interference pattern to occur, to at least some extent, light must be trying out alternative routes through time. It's a mind-bending result. And sadly, for our aching minds, it's not the only experiment to suggest this.
Can information travel backwards in time? It's the sort of thing that would be really useful. You could warn your past self about a mistake. You could reveal the winning lottery numbers. But it just doesn't happen. The resulting paradoxes would make the whole thing laughable. In our universe, time always seems to flow in one direction, forward. The idea seems so outlandish, it can't possibly be true. So why is it that on the quantum level, information seems to be doing just this? To demonstrate this idea, we need to look at a man named John Stuart Bell and quantum entangled particles. What are entangled particles? In quantum physics, it's possible to hit two particles together in such a way as to link them forever, so that by measuring the one particle, you instantly learn things about the other. For instance, if you entangle two particles and you know that their total spin, a quantum property, adds up to 0, if you measure the first particle and you find that its spin is up, you know instantly that the other particle's spin, even if it's billions of miles away, is down. On the surface, this isn't that weird. Einstein famously hated this idea. He called it spooky action at a distance. But he thought he had a simple, common-sense explanation. He called it hidden variables. He said, the particles are like a pair of gloves. If I take a pair of gloves, I put one in a box and one in another box. I mail one box to China, and I open my box here in America, and I find the left glove, I instantly know with 100% certainty that the box in China contains the right glove. No spooky action was needed. No information traveled faster than light. The information, which glove was which, was always there from the very beginning. This is what Einstein thought was happening. It turned out Einstein was wrong. Because, as it happens, the particles are not like gloves. They are not left or right until you look. This is the strange thing about quantum physics. Just like in the double-slit experiment, particles do not have fixed properties until you detect those properties. A particle's position is a wave of probability. Well, so is its spin. John Stuart Bell was a physicist who conceptualized an experiment to test this. Was Einstein right? The gloves theory, hidden variables? Or was quantum mechanics right? The spooky theory, where particles are making it up on the spot. The math is very complicated, but the result is not. The experiment, called a Bell test, has been run hundreds of times, and every single time, quantum mechanics wins. Einstein was wrong. The particles are, apparently, making up their spin on the spot. Which is spooky, because not only does that call into question our perception of reality, it also means that the moment one particle decided on its spin, its quantum entangled partner instantly knew that that decision had happened. You could test both particles at the exact same time, no matter the distance, and the same result would come back. Somehow, information had traveled from the one particle to the other in no time at all, far faster than light itself. This already seems to break everything, but we can take this one final, terrifying step and have information going back in time.
This is our final experiment. It is known as the delayed choice quantum eraser. Its primary purpose was to explore that fundamental question: when does light decide to be a wave or a particle? In the double-slit experiment, light seemed to choose its path depending on whether it was observed at the slits. In 2006, a number of scientists asked a terrifying question. What would happen if you tried to observe the light after it had already gone through the slits and supposedly picked a path? Consider this experiment. A single photon is sent into a beam splitter. It has a 50-50 chance of either being allowed to carry on along path 1 or getting reflected up along path 2. Once on either path, the photon is bounced off mirrors and both paths reconverge at a second beam splitter. Here, once again, the photon has a 50-50 chance to go either way, with an even chance of arriving at one of two detectors. If light were just a particle, this is simple. It would have an even chance of arriving at either detector. But this is not what happens when that second beam splitter is present. When it's present, the light produces an interference pattern. This is strong evidence that the single photon went down both paths at once, like a wave, and interfered with itself at that second beam splitter. Okay, so with the second splitter in, light is a wave. But what happens if you remove that second beam splitter? Suddenly, you can know which path the light traveled. If light arrives at the top detector, it must have come from path 1. If it arrives at the side detector, it must have come from path 2. And something about this knowledge spooks the light. The moment you remove that second splitter, the light stops going down both paths. The interference pattern vanishes, and suddenly each photon only arrives at one detector. It behaves like a particle. So, here is the delayed choice question. What happens if you randomly insert or remove that second beam splitter after the photon has already passed the first beam splitter and has already supposedly started down one or both routes? You are delaying the choice of how you will detect the photon until after it has already committed to a path. What happens to the light? What happens is a very, very strange thing. When this experiment was performed, the results came back unequivocal. If the beam splitter was present in the future, the photon in the past suddenly and seemingly retroactively stopped picking a path and went down both in order to create the interference pattern that it knew it would need to make. If the beam splitter was removed in the future, the photon in the past seemingly knew it would later be detected, and it picked a specific path to accommodate. Let me say that one more time. Somehow, the choice of whether to add or remove the beam splitter in the future changed what the photon did in the past. So, what is happening here? Is it really true that particles can somehow see the future? Did this experiment cause information to be sent back into the past? Or is there some other, deeper quantum principle at play here that we just don't understand? A principle where perhaps on the quantum level, time simply does not apply, and past and future are meaningless. We don't know. But until then, we just have to all agree on one single thing. Quantum physics is strange. And our final mystery proves that we don't even have to look that deep to be baffled. Sometimes the universe puts the puzzle right in front of our faces. Sometimes coincidences aren't coincidences at all. Imagine a game of pool. The balls are in a triangle. The player shoots. The balls scatter, but then, against all probability, they all start falling into the same hole at the same corner. What would you think? A fluke? Or would you start checking under the table to see if someone is rigging the game? Now, think about our solar system. Imagine a large mass came screeching into it and knocked out 2 planets. And those 2 planets headed off in the same direction at the same speed and started orbiting each other in deep space. The odds are astronomical. And so, it's not a complete surprise that the James Webb Telescope has found an example of this. In the Orion Nebula, 2 planets, each the size of Jupiter, are orbiting each other. Scientists call them Jupiter mass binary objects, or jumbos. But the Webb telescope didn't find one example of jumbos. It found 40. It surveyed 540 planetary mass objects, and 9%, almost 1 in 10, were jumbos. That is not just unlikely, that is downright suspicious. It is so suspicious that it's time to start checking the legs of the universe. Because one thing scientists all agree on, our models for how stars and planets are formed are
certainly wrong. And in 2022, astronomers found a new radio signal arriving every 22 minutes. It looks like a pulsar, a dead, spinning neutron star, but it has been stable since at least 1988. A pulsar rotating that slowly should be dead. It should be silent. It's in the death valley. And yet, we are detecting it. It should not be shining. So what is it? A magnetar? A white dwarf? None of our theories can explain the 22-minute signal. We are surrounded by mysteries. From LFB bots, to dark energy, to jumbos, to signals that should not exist. We are just beginning to ask the right questions. And whatever the answers are, we are sure to learn of an entirely new phenomenon that we have never seen before. Isn't that exciting? What do you think is the source of the 22-minute signal? Let me know your best theory in the comments below. Thank you for watching this entire journey. It was a long one. And, as we promised, for those of you who made it this far, we will now be making our donation to help fund the next generation of explorers who will one day find these answers. Your curiosity and your attention have real power. Never stop questioning. Thanks for watching. We'll see you in the next mystery.